All right, welcome to another exciting episode of Advanced Level Chemistry here at Spain Park High School. Today is Tuesday, September the 10th, and we're going to be talking about heat versus temperature. And if you're enjoying these exciting videos, Jacob, what are they supposed to do?
Hit that like button and smash that subscribe button.
That's exactly right. And even ring that bell for notifications. Here we go. All right. So we've been talking about heat versus temperature, and I don't have my thermometers up there anymore, but what is temperature measured in?
How fast?
What unit is it measured in? In degrees. What units? What degrees? Celsius or Kelvin? And how are Kelvin and Celsius related? Okay, a change of 1 degrees Celsius is the same as a change of 1 Kelvin, but how do we convert Celsius to Kelvin?
Plus 273.
Plus 273, very good. All right, now we have the Fahrenheit and the Rankine scales, but those are the English scales, and we don't hardly ever use those. We're never going to have to go Fahrenheit to Celsius back and forth, but we did kind of see where that 9/5 ratio came from the differences in the divisions. Okay, so what does temperature actually measure then?
How fast?
How fast they're moving, and what type of energy is that?
Kinetic.
That's the kinetic energy. Now, it's the average kinetic energy. So again, in this beaker, some are going fast, some are going slow, but there's an average. But as I'm heating it up right now, the average kinetic energy is increasing. The molecules are moving faster. Heat them up, speed them up. Cool them down, slow them down. All right? But then, sometimes, though, we have phase changes. Phase changes involve the breaking of bonds and the forming of bonds. Does that change how fast the molecules are moving? Let me give you a hint. No. It changes their position. And what type of energy is it when we change the position? Potential. Breaking bonds and forming bonds is always potential energy, which we call latent heat. What does the word latent mean? Hidden. What's it hidden to?
Thermometer.
The thermometer. Because the temperature only measures changes in kinetic energy, not changes in potential energy. Okay? So we have, when we're changing temperature, it's a change in our kinetic energy. But when we're changing phase, breaking bonds and forming bonds, it's a change in potential energy. Change in kinetic energy, a change in potential energy, and then your change in kinetic energy. So there's a relationship then between heat and temperature, but not every time when you add heat does the temperature change. We have 2 ways of measuring that. And we have this thing called the specific heat. And we talked yesterday about the specific heat being the ratio of how much heat does it take to cause a specific temperature change. And I used the example of $100 going to Old Navy or Saks Fifth Avenue. Because the shirts are cheaper at Old Navy, for the same amount of money, you get a whole lot more shirts at Old Navy than you can at Saks. Same thing here. If I compare the specific heat of aluminum, which is 0.9, to the specific heat of water, which is 4, roughly 4.184, a degree costs way more to change water's temperature. So for the same 100 joules of energy, you're going to get a whole lot more temperature change for aluminum than you are for water. It takes a lot of energy to heat up water. So we're going to look today at how to calculate this. So in our equation for specific heat is equal to your heat divided by the mass times what's this triangle mean?
Change.
Change in what letter is it?
Delta.
It's a Greek letter delta. Okay, change in temperature. But we can rearrange that to Q equals MCAT. It's got a little bit better ring to it. Q equals MCAT, just the easier way just to remember that. Now the equation will probably always be given to you, but still just Q equals MCAT is the way we can do that. So we want to practice then that this is always your heat. We need to always make sure we know Q is the heat, C is your specific heat. Okay, so I want us just to practice seeing how we can use that equation. Then we're going to do a classroom lab, okay, where I'm going to kind of do it, but you're going to take the data, and then we're going to look at the calculations of that and make sure that we know how to do all of that. 1, 2, See if I get a lucky guess on torque. There's actually a question about it. See me that is. See me that is. Good torque? One extra?
One extra.
One extra? We got it. All right, so let's look at number 23 on this. In number 23, number 23 says, as we pull this up, the specific heat capacity of aluminum is 0.9 joules per gram degree Celsius. Okay, now, well, I'll have to say that in a second. Calculate the energy needed to raise the temperature of an 8.50 times 10 to the 2 gram block of aluminum from 22.8 to 94.6. Okay, so we read that and there's a bunch of numbers, a bunch of words, but let's just isolate here. The specific heat capacity of aluminum, notice the units, joules per degree Celsius times grams. Okay, so what letter in my equation in Q equals MCAT, MC delta T, which letter, when it says specific heat capacity, is this? What letter is that? That's C, correct? And so I would maybe even circle that and put C by it and make sure that you know that that's C. And then the question says calculate the energy needed to raise the temperature. So which letter is that energy going to be? In our Q equals MCAT, which one is energy? I'm just hearing mumbles. I didn't hear it for sure. What letter is energy? Q. Q is, again, if you remember, Q is going to be our heat in joules. Heat and energy are the same thing. Okay? So it's really important. You know what you're looking for. There's an old saying that I made up not too long ago that says, if you don't know what you're looking for, you'll probably never find it. Right? So I know I'm looking for Q. So again, I would circle this right here, and I would just say Q, and I'm going to just put a line to it. That's Q. Make sure you know energy. When you says calculate the energy, when you're looking for energy, you're looking for Q. Q, I don't know where the letter comes from, why it's Q. There's some Latin word that starts with Q for energy or something. I've never known where the letter Q, but Q always represents heat. Heat and energy. Heat's a form of energy. So I know I'm looking for heat. I'm given the specific heat, 0.9. I'm given the mass. What is this just going to be in normal notation? 8.50 times 10 to the 2.
850.
850, right? Now, is that zero significant? 8.50?
Yeah.
It is, right? So I can write that. Q is equal to 850. So how do I make that zero significant if I just write it out?
As decimal.
Add my decimal. The specific heat is given. The specific heat capacity is 0.9. Now, y'all, in all my time of doing this, I always say grams degree Celsius. Is there any difference? They say degrees Celsius times grams. Is there any difference whether you say grams times degrees Celsius or degrees Celsius times grams? No. Okay, so don't stress over that fact that I'm making this unit slightly different. You know, I'm just putting them in different orders just because it's hard to teach an old dog new tricks, and I always just say grams degrees Celsius. That's how it is in my brain. Okay? And then, what does delta T mean? Change in the temperature. You need to know delta T is always T final minus T initial. You always subtract it. In this case, it's getting hotter, so the temperature is going up, so a change in temperature is going to be positive. But sometimes we're going to find when we're coming down, as you're cooling things down, things get colder, the temp change in temperature will be negative, and we can keep that negative sign in there. We don't want absolute value. It's always T final minus T initial. So we're gonna go 94.6 degrees Celsius minus 22.8 degrees Celsius. Okay? Now remember, for sig figs, you gotta do the subtraction in the parenthesis first. Now that's gonna come out to still 3 sig figs, right? It's still gonna be a big number, okay? So, somebody on your calculator,
71.8.
71.8?
For just the subtraction.
Oh, that's just the subtraction part, okay. I was gonna say, that's a small number there. So this comes out to 71.8 degrees Celsius. And again, if you, I prefer you put it in there like this, but if you just do it and then plug in the number, you know, we can see where it comes from. So when you plug all that in, then what do we get?
54,927.
54,900 and what?
27.
27 joules, but that should be to how many sig figs? 3, so what does that round to 3 sig figs? That's right, 54,900 joules. And then, just out of curiosity, what would that be in kilojoules? How many kilojoules would that be? Right, there's 1,000 joules in a kilojoule, so we're just gonna divide by 1,000. That's the wonderful thing, again, we don't have to change the number, we just move the decimal point, and so we're gonna know that kilo is 1,000, so it's gonna be 54.9 kilojoules. Sometimes when we have these big numbers of joules, we want to express it in kilojoules. Now the problem didn't say that to do that, so either one would be fine, but just, we're gonna get comfortable just making those conversions just in our head. All right, so again, it's just Q equals MCAT. It's just plugging in. We have 4 variables. Generally, you're going to be given 3. You just need to make sure you know what each thing in the problem represents. That heat is always going to be Q, specific heat is going to be C. Your change in temperature is always going to be final minus initial. So right now, just in your notes, just practice and see if you can do 24 B and C. I wish I could pause the video right now for those of you watching around the world, but you can feel free just to fast forward through this pause until we get to, or work the problem on your own, and then when you're finished, fast forward till we start going over this. I'm sure somebody in Australia is going to want to watch this.
You can probably do some like editing. Just like
Yeah, you can edit it out.
It takes too much energy. I just don't I don't have time for all that. I'm not trying to make money. I'm spending my time breaking y'all's lab, not editing video. All you guys cramming it into a tiny space rather than getting out a piece of paper and doing notes. You have a whole packet of notes for specific heat. So what do we think? We done? All right, so let's look at, again, one of the things I want us to do is just to practice analyzing the question. When you have a whole bunch of numbers and words that you're not familiar with, we just need to look at what am I given, what am I looking for? So the specific heat capacity, as soon as I see this word specific heat, that's going to be your indicator, Q equals MCAT. Almost always, but if you have a problem that mentions the term specific heat, it's going to be a Q equals MCAT problem. Just as far as, ding, 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 how do I set this up, what do I need to do? So as soon as you see a problem that says specific heat capacity, Q equals MCAT. So what is the 0.71? Which letter is that going to be? C. Okay? And calculate the energy required. So again, I'm going to be looking for
Q.
Q. So I'm going to say this is now going to be 24. B. Q is going to equal the mass. Now this time, is the 0 and 850 significant? No. Okay, it is not. So I'm just going to say 850 grams with no decimal point. The specific heat is 0.71 joules per gram degrees Celsius. And what's my change in temperature? Now this time they just tell you the change in temperature directly, correct? It just says the temperature changed by 150 degrees. So it's important again that you look at, is it talking about an initial and a final temperature, or is it talking about the temperature change? You take English classes so you can learn how to interpret and read and accurately deduce what's given and what you're looking for in a chemistry problem. Okay? That's the main reason you take English, so you can get a chemistry problem answered correctly. So we know it's just going to be 150 degrees. Now, how many sig figs are there in all three of these measurements? Just two. So what does our answer come out to? What's the whole thing come out to if you don't round off? Can anybody write the whole thing down?
It's like 905 something.
Say that again loud and read here. 90,525. Did I hear it right? Okay. So I need to round that to 2 sig figs. So I'm going to go 1, 2. Since this is a 5, I'm going to say what? 91,000 joules, which is how many kilojoules?
91.
91 kilojoules. All right? Not too bad? So the specific heat gives us the ratio between how much heat do we add versus what's the temperature change going to be for a given mass of the substance. Okay? If we have some other metal, this number is going to be different, so the temperature change would be different. All right, last one, C. Just need to make a point with this one. So we're looking at C. So again, we're looking for Q, but there were 75 kilograms. Can I use kilograms? No. Now, I know that the SI unit for mass is kilograms. So how do I know if I'm supposed to use grams, kilograms? Because on the other ones, you always said I had to use kilograms. Always go to the constant. And whatever the units are on this thing here, that's the units you have to use on everything else. Okay? So, because it's in grams here, I have to use grams for M in my mass. Okay? So you can always look to the units. Again, units are always going to be your friends. Units are going to help you. They're going to tell you what to do, how to set things up, you know, what unit you have to use. So how many grams is 75 kilograms? 75,000. The specific heat is still 0.71 joules per gram degree Celsius. Now, it says that it goes from 294K to 348K. Do I need to change that to Celsius? Why not? Fix, go ahead.
Because it takes the same amount of energy to raise 1 degree Celsius.
the change is gonna be the same. Think about it mathematically. If I subtract 273 from this and 273 from that, when I subtract, the difference is still gonna be the exact same number, right? So as long as it says delta T, the change in the temperature, you can use Celsius or Kelvin, you don't have to change. Now, it's not wrong if you did, it's just an extra step, you just don't have to. So it's going to end up being, final minus initial is 348, okay, minus 294K. So when you do all of that, what's the answer come out to? 2,875,500 joules, but how many sig figs should I have? 2. All right, so what's that going to round to?
29,000.
Joules, right? And that's going to be, move to 3 places, 2,900 kilojoules. Right? Does that make sense? All right. So now let's look at, I just passed out to you a lab sheet that we're going to kind of do together on how can we experimentally calculate this specific heat. Okay? What can we do here? And as you follow through on the procedure, okay, I've already kind of started in on some of it. It says add 250 to a 400 ml beaker. Here's my boiling water bath. I just added some water. We have a boiling water bath. It's now boiling. So what temperature is it in here? 100 degrees, right? Now I'm going to take, then it says, once the water is boiling, tie a piece of thread around a metal sample and carefully, okay, so I'm going to put it into, well, first thing I need to do is I need to weigh it. Okay, so this is the mass, and this is copper, so I'm going to weigh this. And it comes out to 149.67. I'm going to do it one more time because it was a little bit different before. Okay, 149, we'll go 0.66. 149.66 grams. And now I'm going to put it into the boiling water bath. So what temperature will the copper get to? 100 degrees. Okay? So now let's just kind of turn it over and let's look at it. We'll just kind of go through it. I'm going to follow the procedure here, but we're just going to fill in the data table. So the mass of the metal, we're doing copper. What was the mass of the metal? What I just said? 149.66. So go ahead and fill that in right here. Ooh, my string fell in. Might burn. Oh, it did burn. It's all right. So now it says the mass of the dry cup, because we're going to make, this is what we call a simple calorimeter. It's going to be this beaker here that's going to be kind of trapped air, and then we're going to set this inside of it, so it's kind of going to get double insulated, but we're going to put the water inside of here. Now we technically could just measure the volume, and we know the density of water is 1, so if I put 100 milliliters, that would be 100 grams. But I want to just weigh and get the exact amount of that. So I don't need the mass of the cup. We're assuming the cup absorbs 0 energy. It's styrofoam. We're going to make a false assumption that it is 100% insulator, not absorbing any. And I need that air conditioner to turn off because it's really messing with this. But this cup says that it's 4.00 grams. So the mass of the dry cup. Now I'm going to add about 200 milliliters of water. But I'm not going to have to be perfectly exact because I'm going to weigh the mass. So there's about 100. That should be about 100 grams. But I need to make sure there's enough water in there to cover up the piece of metal. Okay? There's close to another 100, it's a little bit less. Crud. Now I got water on the outside and we don't want that, so I gotta dry that. My hand's wet. Alright, so now the mass of the cup and the water is 199.97. 199.97. So how do we get the mass of the water? Just subtract it out, right? So now I'm going to set that into here. Okay? And I'm going to go now and I'm going to put my temperature probe into here. And I'm going to let you guys kind of see, what does the temperature say? Can we read it? 24.6 degrees is my initial temperature of the water in the cup. 24.6 degrees right here. Okay? 24.6. Now let's see. So we're assuming now, I gotta try and grab the string. Now I'm going to take this, and I'm going to quickly transfer it to here. Okay? Ready? 1, 2, 3, go. Now I'm going to stir it, just because I want the water to heat evenly. So what's happening to the water?
It's gonna get hotter.
It's getting hotter. What's happening to the copper metal?
It's gonna get colder.
When's it going to swap or stop changing? To zero?
When they become the same.
When
When they get the same.
When they get the same temperature. Okay, when the change is zero between the two. Okay? We're going to call it fancy term. Thermal equilibrium. Simple terms, same temperature. Fancy terms, thermal equilibrium. Simple terms, same temperature. Now is the temperature still going up? Is it changing at all?
A little bit, not really.
Okay, is it just fluctuating back and forth?
29.3.
What is it?
29.3.
So it's you feel like it's pretty constant now?
Yeah.
Okay? 29.3 is our final temperature.
Yes.
Okay? So what was the initial temperature of the metal?
100.
We're assuming it was 100 degrees. Okay? I didn't measure it with the temperature probe. We're just going to assume it's 100. Okay? So the maximum temperature reached here is the 29.3. So now let's talk about, what do we know? Oops, wasted water. Well, I'm going to hold this. So we can determine the change in temperature. Well, before we even do that, what's the premise then here? Why did the water get hot? Because the hot copper was placed into it. What do we know about the direction of heat flow?
Goes from hot to cold.
Hot to cold, right? So where was the heat flowing from and to? From the copper to the water. Now we're making an assumption that only the water absorbed the heat, only the copper lost it, okay? And so we're just going to kind of go from there. What law are we kind of talking about? If the copper lost but the water gained,
Matter or energy can't be created or destroyed.
okay, that's the first law. It's
Conservation of
it's
matter.
the first law of thermodynamics. It's the law of conservation of energy. You've learned this your whole life. Energy can neither be created nor destroyed, right? If something gains energy, if something loses energy, something else has to gain the energy. It doesn't just disappear. You can't create it, you can't just make it go away, it just changes. So the first law of thermodynamics, and we'll just write it like this. That's the conservation of energy. And we don't need to write out what it is. Everybody, I think if I just say conservation of energy, you all know energy is neither created nor destroyed. It just changes form, right? So you don't need to write it all out. Just conservation of energy. But let's talk about how we represent that mathematically. Well, mathematically, we're going to say that the Q lost by the copper is going to equal the negative of the Q gained by the water. Q lost is always equal to negative Q gained. Now, what does the sign mean? The sign simply means the direction of the heat flow. You don't have negative energy. Some of y'all might have in here as you're trying to stay awake, but as I see it gone. Okay, negative energy. Negative simply means that energy is being released. Okay, positive means that energy is going in. Okay, so if something is gaining energy, it's going to have a positive value. If something is losing energy, it's going to have a negative value. Okay, does that make sense? Are you with me so far? So the lost energy is going to be the negative sign of whatever was gained here. So what gained the heat in our demo? The water. What lost the heat? So the Q of the copper is going to be the negative of the Q of whatever the water. So however much water, heat energy that the water gained, we put the negative sign over here, that's going to be how much the copper lost. Okay? And the sign just simply tells me the direction of heat flow. And that's why the change in temperature is going to be really important, because it's going to help us with the sign. All right, well, how do we get Q of copper? How do you find the Q, or the heat change, where the heat gained or lost when there's a temperature change? What's our equation? Q equals MK. So I can say the mass of the copper times the specific heat of the copper times the change in temperature of the copper is going to equal the negative. Well, how do I find the Q of the amount of energy of the water gained? Go ahead and say it, Fury. You're thinking it. Yeah, I thought you were about to mouth it. If this is going to give me the heat lost by the copper, how do I find the heat gained by the water? MK. But this time it's going to be the mass of the water times specific heat of the water times the change in temperature of the water. Q lost of the copper is going to equal the negative of whatever heat was gained by the water. This is how a calorimeter works. We saw the picture of the bomb calorimeter earlier in the unit, and when you burn that Snickers bar, the energy lost by the Snickers bar is going to be the same as whatever was gained by the water around the Snickers bar where it was burned in that bomb calorimeter. A calorimeter measures the calories, because the heat lost by the reaction is gained by the water surrounding it. The law of conservation of energy. Are you following me on all that? Q lost is always going to equal Q gained. This is conservation of energy.
Is everything negative, like on the second one, like the N, the C, and the T?
Well, yeah, I mean, it's just math that's going to distribute through. So, but it's not negative, 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 because then they all start canceling each other out. It's like this.
Okay, that makes sense.
Okay? So now, what's the mass of the copper? What did we say the mass of the copper was?
149.66 grams.
149.66 grams. Our goal is to find the specific heat of the copper. Well, what was the change in temperature of the copper? Well, no, it started at 100. What did it end at? 29.3, right? And it's always going to be final minus initial. So it's going to be 29.3 degrees Celsius minus the 100 degrees Celsius. And that's going to equal, and we can go ahead and say the negative if you want to put the parenthesis there. What was the mass of the water in the cup?
The same as
195.
Okay,
970.
okay, because there was one. How much was? What was the total with the water and the cup?
199.
199. But we had to subtract the 4, right? The mass of the cup. So what did that come out to, Mia?
195.97 grams.
0.97 grams. That's how much water was actually in the cup. Now, what do we know the specific heat of water is in joules? It's 1 calorie. Do you remember the conversion factor between calories and joules? You're very close. It's 4.1. Okay, now this number is going to be given. You don't have to memorize it. 4.184. Okay? Given, and it's the specific heat of water. Just, again, just so you know what every number is. Okay? So this is the mass of the water in the cup. This is the specific heat. It's a constant. Water is always that. And what's my change in temperature of the water? What was the final temperature of the water in the cup? 29.3 degrees minus, what did it start at? 24.6. Okay? So now it's all over but the shouting. Now we just have to plug and chug and just solve for C. Do we want to do what the delta T's are individually first? Just to make the math easier for you. So this one obviously is going to be 70.7. This one is going to be 4.7. So it's just going to be this times 4.7 divided by 149.66 divided by 70.7. So the specific heat of copper, experimentally determined, always hope we're close. And everybody needs to be writing all this down because I will collect this as a classwork grade. I'm kind of going through, I'm doing the calculations kind of all at once. The calculations kind of break it down into individual parts, like the left side of the equation and the right side of the equation. Y'all are slow on the calculator. Nobody just wants to say the answer. Did you get some? No? Anyone want to venture a value? 0.36.
42.
Okay, so we should probably only have, well, we have 5 sig figs, 3 sig figs, 5, 4, and 2. Okay, so how many should we have?
2.
Just 2. So 0.36, what's the next digit? 4. Okay, so 0.36, and the units, notice here, okay, grams and degrees Celsius do not cancel. Okay, so there's nothing going to cancel over here because we don't have any units on C. That's an X. That's an unknown. Over here, grams cancel with grams. Degrees Celsius cancel with degrees Celsius. It's really only that one. So we're left with joules over on the right-hand side, and then you're going to divide by grams and degrees Celsius, right? So we're ending up with joules per gram degrees Celsius, which are the units on specific heat. So we got 0.36. Now when you go and you look on your periodic table, on the back side of your periodic table, you find that the actual value of copper is 0.385. Okay? But to make my percent error better, I'm just gonna round that to 0.38. Okay, because this was 0.364, I think. So just to kind of balance things out, we're gonna go 0.36 and 0.38. So how do I get my percent error? If the correct answer is 0.38,
The value we got minus the actual.
okay? So 0.36 minus 0.38 divided by 0.38, always the right answer, times 100. So, what does that come out to?
Negative 5.26.
Okay, now this is one that I really wanted to count sig figs, you know, and whatever, but on your labs that I'm grading, but they were all so bad that I ended up not doing it. But how many sig figs should there be?
2.
1. Why 1? What do you get when you subtract this? Negative 0.02. How many sig figs is that? Only 1. So this should really, you're going to say, negative 5% error. Now the reality is that that's really pretty good. Because what are some of the sources of error in this? What are some things that are going to maybe make us not get exact answer based upon how we did this lab? Yeah.
Assuming the temperature of the metal.
We had to assume it was actually 100. Okay, it was sitting on the bottom. Could have been a little bit warmer. Maybe it didn't sit in there long enough. Now we're under. So what value needed to be bigger in order to make this number bigger? Do you think the mass was really that far off? Assuming, yeah, we just weighed on the balance, that wasn't a big deal. Okay? Again, the mass of the water was probably pretty accurate. Which number would need to be bigger to get us to 0.38? The temperature. Probably this temperature right here. Okay, because if this one went up, this number is going to be bigger. If that number went up, this number is going to be smaller. So we're going to have a bigger number in the numerator and a smaller number in the denominator. So it didn't go up quite as much as it should have been. Why not?
The styrofoam cup probably took some heat out of it.
The styrofoam cup could have absorbed some heat. Do we have a lid on it? So what would the effect would that have? Maybe some of the heat left out of the top. It's not perfectly insulated. How did I transfer it? Through the air, right? Did any heat get lost as I transferred it through the air? Possibly. Now, it was on the other side of that, it was still wet with hot water. So I did bring some hot water in here as well. So if I measure this now, there's a little bit more water in here because the metal was still wet. I couldn't go and dry it off because that would make too much heat lost. Okay, but it's a very simple, but we can see the point that I want us to get from this. What I want us to get from this is Q lost equals negative Q gained. The first law of thermodynamics. Heat lost by something hot is going to be gained by something cold. Okay? Q lost equals negative Q gained. All right, it was a good day today, and I will bring all this tomorrow, and we'll just talk about what all needs to be done on this tomorrow. It's not due tomorrow. Okay? This is not due tomorrow. All right, have a good one.